Okay, so to start with, so what is process mining? When we consider process mining, normally we tend to use data, so historical data, or in certain cases even live data, so data that come from processes that are currently under execution. And by using process mining algorithm, we try to gain some sort of like actionable process knowledge. So some knowledge that can be of use for us on the moment. And this knowledge can come in the form of process models, in the form of like information about the performances of our processes. We may want to know if, for example, our processes are conformant, so compliant with, I don't know, internal regulation or regulation that may come from, let's say, from the government or this type of things. Or finally, we may want to use process mining to, I don't know, identify if there are differences between cohort of data that we have, or let's say identify root causes of problems and all these type of things. And these four outputs basically can be categorized in four major groups of process mining. So that if we are trying to discover process models, basically what we are dealing with is the automated process discovery. Then we can deal with process performance analysis when we are focusing on the performances of our processes. If you are trying to identify if the processes are compliant or not, we tend to deal with conformance analysis. And if you are looking for root causes or differences between logs, normally we deal with variance and deviance analysis. And in this talk, we will focus on the first group, which is often the aspect of process mining that the majority of people are exposed to. Because normally when we have an event log, the first thing we do, we load it in one of our process mining tools, and we try to discover a process model out of it so that we can have a graphical representation of what's going on into our system. So, and a log, in general, what we need can contain a lot of information. So logs normally are sequences of events containing multiple information, any sort of information that is produced throughout the execution of a process. But in general, we need at least three essential information. The first one, it's a case ID, which basically it's what allows us to group events together to say, okay, all those events belong to the same case. So for example, all the things that we have done it for this particular student, or we have done it for this particular patient, and this type of things. Another thing we want to know is the concept of activity. So every event represents something that we have done. What is this something? So it could be like, in this case, we are registering a request, we are examining something, we are checking the ticket, we're making a decision, and we are rejecting the request. So basically, information that let us know what each event represents. And finally, we need a timestamp. The timestamp basically allows us to understand in which order things are happening. And once we have these three things, technically, this is all we need to conduct process mining. Of course, the more we have, the better. So if we also have information about resources, then we can explore things such as social network analysis and see, for example, how our, the employee involved in the process are interacting with each other and this type of things. But they are not essential information. And in general, when we consider process mining, we see it almost as a black box. We feed in the event log, and magic, we get a process model in output. Or at least this is what we will hope to obtain. In reality, often we get something like this. It's a mess where we have like arcs going almost from everywhere to everywhere. And I believe that you agree with me that models that look like this are not really useful, because basically they do not help us to understand what's going on in the system, what is going on in our processes. They are extremely confusing and do not really transfer any knowledge back to us. And the question is then, it's how can verify if a model that we discover it's a good or bad model. So in general, in this case, we tend to use four quality dimensions that are fitness, precision, simplicity, and generalization. So fitness basically tells us is my model capable of reproducing everything that is in the log? The more my model can reproduce what the behavior that is in the log, the higher the fitness values should be. Simplicity basically means literally how simple is my model. So the model that we saw before with all those lines clearly will score really badly on a simplicity level, simply because it's messy, it's difficult to understand, so it's the opposite of simple. Precision basically tells us the model, the behavior that our model represents, how close is to the behavior in the log. For example, can the behavior in the model produce behavior that in the log does not exist? So can the model allow me to do things that I never observe in the log? If this is possible, then means the precision goes down, because it means that my model allows me to do things that in reality I never done. So for example, let's say I always perform, I don't know, I wake up, I drink my coffee, and I brush my teeth. That's every day I follow these two actions in this order. And my model tells me, oh, you know what? You can do the opposite. If you want, you can brush your teeth before drinking your coffee. Or the opposite, doesn't matter. You can do them in any order. In this case, my model will have a low precision because basically it allows me to do things that in reality I never do. And the last bit is the concept. So in this case, for example, as the example that I was mentioning before, in the log, we are always observing A followed by B, A followed by B, A followed by B. And in this case, for the one of you that are not familiar with the BPMN notation, basically, these are gateways that basically are, let's say, decision point. And in particular, this is our end gateway. So it's a decision point that allows me to execute these two activities concurrently. So let's say, theoretically at the same time, and basically means that we are always doing both A and B, and we can do them in any order, which basically it's not what we see in the log. The last aspect is the concept of generalization, which basically tells us, okay, my model can reproduce the behavior that is in the log, but if the behavior, let's say it's a slightly extension of what we see, without anything crazy like imprecision, am I still good enough or not? So for example, in this case, in my log, I see that I can perform the activity A. Sometimes I can do activity A 2 times. I can do activity A 3 times. Then a model that allows for generalization will assume that theoretically, it's not unusual to assume that you can perform A 4 times or 5 and so on. So basically, in this case, we are modeling A in a loop. So these are the 4 dimensions. And ideally, when you do basically an analysis, you would like to have a model where these 4 dimensions, they are all scoring the highest value possible. How can we do to basically obtain such results? Well, in this, from my point of view, we can operate at 3 levels. So the first level is that we can do some sort of pre-processing. So in pre-processing means like you may try to clean, to improve the event log by removing information that is not essential, that is not useful, that it's sometimes considered noise, or if you are more familiar with the concept of, let's say, data mining could be, let's say, outliers for this type of things. You can do something at the level of the discovery, basically the algorithm that you're using, or you can do something as a post-processing phase. So basically, after you obtain the model, you can try to work at that stage and try to make some improvement. And we will discuss 3 approaches, but keep in mind that these are 3 approaches that I propose, but you can also come up with your own ideas, so long as basically following these principles. So in the context of pre-processing, I tend to follow the idea that if you have an event log that is garbage, so that there is a lot of like information that is bad information, like noise, so in this case of bad quality, you cannot expect to have a good model. So if you provide bad input, chances are that you will produce bad output. So the idea is like, let's improve the input. So let's try to remove noise. And in this case, for me, noise are events that basically represent infrequent behavior. So things that could be that are recorded in the log, but they are not performed so often to the point that it's worth mentioning them. But if you leave them in the log, they're just going to make the discovery more complicated or the final output more complex, which basically then will have an impact that tend to create a model with a lot of like arcs, a lot of gateways that technically are never executed. Because, for example, like it's only executed once. So what can we do to improve? So in the approach that I proposed, basically the idea was like, allowed me to improve the model that we have here. So basically this is what I was able to discover without applying my technique. After improving, let's say, cleaning the log, I was able to simplify the process and making it more streamlined and more, let's say, easy to read and also more precise. So you can see in this case, we got rid of all these gateways here that basically tell us, okay, you can skip, you can do, you can skip, you can do, and this type of things. And this is because some of those activities were infrequent. So how do I detect infrequent activities? So the idea in this case is that I take an event log, we go through the event log, and what we do, we generate what I call a automaton. So automaton is basically can be considered a graph, a annotated graph. So in this case, we can see that each node represents the activities that we have. Each arc basically represents the sequence. So we see that if we have an arc between A and B, it's because in the log we are observing A followed by B. The number 4 represents, if it's inside the node, means that the activity occurs 4 times. So we can see here we have 4A. And on the arc means that this connection, this A followed by B, it's observed 4 times. So we can see AB, 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 AB. So basically we read the event log and we generate this automaton, this graph. At this point, then what we want to do, we want to remove infrequent arcs. So infrequent arcs are basically arcs that we do not take that often. But when we do so, we want to be able to maintain the connectivity of the graph. Because the point is like, for example, let's say I remove this arc here, the arc that goes from A to B, I am destroying my graph, because then at this point, once I execute A, my graph doesn't allow me to do anything else. So we have to be a bit smart in say, okay, what can I remove, what arcs can I remove, and what should I maintain? Once we do that, so in this case, we remove all the arcs that are infrequent, but that do not damage the connectivity of the graph. So in this case, we had to choose, we either remove the arc that from C goes back to B, or the arc that from C goes to D. So we have to pick one of the two. In this case, I decided to remove the one that goes from C to D. Because at this point, doesn't matter where I am in the graph, I can always reach the end. So I can do A, B, D, A, B, C, B, C, B, D, A, B, B, D, and so on and so forth. Once we have this graph, basically we use this graph to remove specific event from the log. So basically, we cherry pick the events that do not fit this graph. And in this case, basically, what we are doing is, if you use this as a template, we try to read every event, every trace, we try to execute it over here, and if it's not reproducible, we remove it. So the first one, it's A, B, B, D, so A, B, B, D. That's okay, so it can remain. The second one tells us that we have to do A, B, C, D. Let's try if we can do it. I do A, I go to B, I go to C. Okay, no, I cannot go to D anymore, which basically means that the event C should be removed. Because if I remove C, then I can do A, B, D without any problem. And basically, you do this for every single trace. And now, basically, you are filtering your event log, and you are only retaining frequent behavior. So you remove things that do not happen that often, that have the negative effect of producing messy models. To test, we test this approach on a variety of logs. So we use 4 real-life logs and 16 artificial synthetic logs, and we use it on different process discovery technique to see if basically if this approach was working on each technique or only on some of it. And for each one of them, basically what we did, we measured the 4 quality measure that I discussed before. And what we observed is that by filtering, we can see that we managed to get higher precision while before we were not able to. So basically, we were able to somehow push this data point, the purple one, a bit higher in the model and a bit more on the left. Because ideally, this is what we would like to have. This means that everything is fantastic. Unfortunately, in real life, that doesn't happen. But what we want, we don't want numbers that are at the bottom. We want to have them ideally along those lines. And this is one technique, but a simple way that you can apply a similar concept is like, let's say you're doing a process mining analysis. You simply go to the activities that you have in your log. You see there is an activity that only occurs 3 or 4 times. Just remove the activity from the data set without even going, without even relying on anything more complicated than that. In general, this is already something that you can do by yourself and that will allow you to improve the quality of your processes. The second step you can do is basically at the level of the discovery. Now, I'm not sure if you have a preferred algorithm, but what you can do, you can probably, you may be familiar with the alpha algorithm. That is the first algorithm that was being produced. It tends to be the one that has the less, so it's the worst algorithm in terms of like quality of the final algorithm. So one thing that you can do, you can test multiple techniques, different algorithms. In this case, what I did, we created a new technique. And I will quickly basically show you how our technique works. So in case you may be interested, you can also gain some insight on how process discovery techniques tend to work. And they pretty much, they tend to follow similar concepts. And basically, in this case, we have the top one. It's a model that is being discovered using one of the existing techniques. And the model at the bottom is the one that basically has been discovered using the technique that we're proposing there. And you can see again, it's a simpler model. So before we have an easy way to look for simplicity is by counting the number of gateways that you have in your model. The less gateways you have, generally, the simpler is the model. And clearly, you also need to measure the other measures, and we do that as usual at the end of the analysis. How do our techniques work? Again, we start with our event log, and surprise, surprise, also in this case, we work with graph. So in this case, it's a directly follow graph, which is the basic concept, the starting point of every process mining technique. So directly follow graph is basically what it does. It, as we did before, we analyze every single trace that we have in our log. So in this case, basically, this one is a trace, and this number here represents how often we see the trace. And what we do, we generate our graph. It's similar to the graph we saw before, The only difference is that in this graph, we are not annotating the frequency of the activity, because for a directly follow graph, this information is not relevant. As part of this step, we also take record of another information. Basically, we look for short loops, basically sequences of activity that are repeated one after another. Once we have this directly follow graph, basically this is the key point for any sort of process mining thing. In our case, we use this graph and we try to discover concurrency. Concurrency can be, it's one of those topics in process mining that is still like not fully addressed. It's one of the major issues in process mining. There are like some proposal on how to discover concurrency, but there isn't a final answer. In general, the way we discover concurrency is basically it's when we see that two activities, so in this case, let's say two nodes, have this structure here. Like basically from B, I can go to C, from C, I can go back to B. If we have these type of structures, then in general, in process mining, in 90% of the algorithm, they will tell you that, okay, B and C are in parallel. And if you look at this graph and we look at this particular structure, we can say, okay, we have a parallelism between C and B. We have this back and forth also between B and D, back and forth between D and E, sorry, D and E, back and forth between E and G. So basically, we discover all the potential concurrencies that exist in our system. So concurrency is clear to everybody what it means. Type Y if it's like, or like, if, as I said, as Muslim mentioned before, if something is not clear, feel free to ask. I have no issue to clarify concepts. Sometimes I may run too fast because certain concept may be clear to me, but that doesn't mean that it's something that it's clear to everybody. It's clear to me simply because I spent 10 years working on it. But it's normal. It's normal to have question, and it's normal that in certain cases that things are not. So feel free to interrupt me, no issue whatsoever. So once we have this concurrency, then we try to do filtering. You see, we did. Yeah, thank you, Moser. Filtering, it's always a stage that you do. Sometimes you do it on the event log. Some techniques, probably, I'm aware of at least 4 or 5 process mining techniques that apply a filtering, some sort of filtering during the analysis. In this case, the filtering is basically, let's remove certain arcs that are infrequent. In this case, we use a threshold. So let's say that our threshold is, let's say in this case, probably 10. So any arc that is equal or less than 10 would be removed. In this case, we take it. In this case, we removed all the arcs that are related to the concurrency. So you see that the C and B disappear. And we also remove some of the infrequent arcs of 10. So in this case, we used to have 1, 2, 3. Okay, but in this case, it's because they are concurrent. Questions on this? Or we can go to the next stage. I take a silent as a yes. And then, as I said before, now we remove the remaining infrequent connections. So in this case, we remove this last bit. So the bit that from E was going to C. So now this arc disappeared, as well as the one that from C was going to F. So again, everything that doesn't occur that often gets removed because we only make the discovery process more complex, more difficult, which basically results in a complex and difficult to understand process mode. And then now start to be the more complex part. The first part is discovering the gateways, so the splits. And in this case, in our algorithm, what we do, we tend to look for activities that have more than one outgoing arc. So we have A, B, so in this case, A and B. We use our the concurrency relations that we discovered in the previous phase, and we create this map. So this map basically is telling me, okay, I have B, and after B, based by looking at A, I can see that after A, I have the activity B, C, and D. If I consider B, in the future, basically it means that in certain executions, B may see C and D as well. If I look at C, based on the log, I'm only able to see B. And if I look at D, again, relying on the log and on these concurrency relations, I can only observe D. So basically, this is a table that we build throughout the combination of this graph, the concurrency, and the log that we have. And now we analyze this table. How do we analyze it? First of all, we look for relations that in their future, so basically like what we see after this activity has been performed, that have the same activity. This allows us to conclude that if both C and D, after the execution, they are both only seeing the activity B, it means that B and C are mutually exclusive. So either you do C or you do D. You never do the two of them together. So in this case, basically we replace these two rows in one row where these two are merged. And basically we introduce an XOR split before that. And then we repeat the same operation again. In this case, there are no activities that have, there are no rows that have the same future. So at this stage, then we look if there are rows where basically have their cover and their future that is matching. So in this case, we can see this block here, where we have that for this row, the cover of the first matches the future of the second, and the other way around. So basically, this what is telling us is that these two rows, sometimes I see doing B and then CD. This row I see doing CD and then B. Which, what we've seen before, this type of behavior, like you can do them in any order, means that we have an AND gateway. And basically, we repeat this operation until basically we are left with only one single row. Once we do so, we use them to introduce our gateways. So as you seen before here we discover that we have an XOR split between C and D. So basically what we do, we introduce an XOR split here, and then we put an AND split between these two. So between the after A, between B and the XOR that we just introduced. And if you look here, this is exactly matching. So we introduce the XOR, we introduce the AND between the B and this new block, plus, of course, we also have to repeat the operation for the next activity with multiple outgoing arcs. So in this case, we've done it for B, and we introduce E and F, and this time again in XOR. The last part, it's identifying the matching join. And in this case, it's a relatively easy approach. It depends. There are two ways you can approach it. There is a easy way or a more complex one. In this case, we're just going to discuss the easy way. The easy way is basically like you introduce gateways before an activity with multiple incoming arcs. And then what you do, basically you say, okay, in this incoming arc, if I go backward, what gateway do I find? I only find one gateway. Perfect. Then I match the join of the same type of the split. If this was an end split, I introduce an end join. In case I have a more complex scenario, like in this case G, if I go back here, you may find, okay, sometimes I have an AND, an XOR. Here I may go out. So it's a complex situation. I don't know what to use. I will always put an OR join. This is the easiest approach. So you go this way, and now you introduce the gateway for each one of them. So in this case, here we repeated this operation twice. So we were able to identify a matching join for the XOR split. But then at this point, we were confused because if I go back, I have an AND split, but also an XOR split. So like, okay, which one of this is what our test showed. So in this case, we run it with 12 real-life log on a variety of domains. And we compare our techniques with some of the standard process mining techniques, such as inductive miner, heuristic miner, FODINA. And as usual, we measure fitness, precision, generalization, and complexity, which is simplicity. And in this case, our is the green one. And you can see that basically, in general, we tend to be always, not always, but in the majority of the cases, we tend to be the closest to this top corner here. And consider in this case, the top corner is this one, because our metrics cannot go above 1. So here, for charting purposes, we reported 1.1, but quality measure range from 0 to 1. So ideally, this is the best number. We are, in this case, for example, we are the closest to the best number. Here we are among the best one. Same here. Let's see if there is one case where we are. So here, for example, we are questionable. We have a lot of them of our points at this point. Now, takeaway for you, of course, I'm not expecting any of you to develop new algorithms every time, but what you may want to do is like test different discovery algorithms based on the dataset that you have, because the inherent properties of your dataset may lead to different results depending on the analysis that you run. So you may test 1, 2, 3 algorithms, and you pick the best result because certain algorithms are better for certain type of data set, others work better in other scenarios. The last bit of improvement that you can apply to your analysis, it's at a post-processing stage. And in this case, we can think of 2 approaches, vertical scoping or from the point of view of structure. As a vertical scoping, basically it's like the idea of simplifying your model in a divide and conquer approach. So instead of trying to discover a really big process model, try to discover a lot of smaller one. So in this case, for example, this is what you could discover by considering every single activity and every single connection in your process. But if you look at them in a smaller context, you can get it a simplified way. Why? Because we discovered in this case that we were executing multiple instances, of the same sub-process. So within one process, we were executing the same things multiple times in parallel, which basically was creating a lot of confusion. So in this case, what you need a data set, at least for this technique here, but again, you can do it in a different way and it's still possible. In this case, we need in the data certain information that allow us to somehow discover this relationship between a process and its own subprocess. So basically, are you familiar with the concept of subprocesses? Can you type yes or no in the chat just to let me know? Just to know if I have to clarify it or not. Don't feel shy. I don't buy it. Okay. So in this case, for example, by using this concept of subprocesses, we were able to improve this process model from this messy one with a lot of gateways to the following. Now you can see here that we have a lot of subprocesses. And in this case, it means that this simple subprocess of two activities, it's executed. It's like you have a lot of activity of the same time executed in parallel. And clearly what they do, they end up conflicting with something else. So it's difficult to detect them. So in this case, what do? We take our log. And in this case, we have some additional attribute, not just the basic free one. So here, this is why we need a data set that is a richer data set. And in this case, we need attribute that will represent a primary key, like in a database. And you don't have to specify which one is the primary key. We have already to identify what a primary key is, as well as we need to identify potential attributes that represent a foreign key within the database. Once we have these two, basically we are able to understand, to identify that there is a relationship between this table here and those two elements. So they basically say, okay, this event here has a foreign key that is pointing to these two activities. It basically means that it's a subprocess. Once we do that, basically what we do, we split the log by removing all the events that are relevant to a subprocess. So basically we cluster them, we remove them from the log, and now we analyze the log by focusing on these smaller pieces of our problem. Because now we remove all the events that were part of a subprocess, we're basically making our life more difficult when discovering something. And when we look at them in isolation, it's easier because they are less, they're only working among themselves. They have theoretically a different primary key. So basically means that now we are not seeing traces of, let's say, 20 events. You're only seeing traces of 4 or 5. So it's easier. And so as I said, we split them. Once we have all of them, for each one of those subprocesses, we discover the model. And in our case, we also discover additional elements such as a boundary event that represent potential exceptions. And we try also to identify if those exceptions are due to a timer or to, let's say, messages that we are receiving. We identify, this is another type of subprocesses that are basically, they are triggered by events. And we also identify the type of markers in them. So this may not be that relevant for the scope of this discussion, but just for the sake of clarity, so since we are all these markers. Once you have all these pieces, we basically reglue all these smaller processes together. Let's see, like in this case. So if you look at them, basically what we did, we discovered a process only for those two activities. We discover a process just for this one. We discover a process just for this one. We discover a process just for this one. So they were really smaller pieces that then we basically glue together to get our complex scenario. We test it with 2 real-life logs and 1 synthetic one, and we use our approach on top of several existing algorithms to see if basically, since it's done after the discovery it's used, so it doesn't matter which discovery algorithm you use. And as usual, we measure the 4 dimensions. And also in this case, basically, by using hierarchy, which allow us to somehow indirectly filter out noise or infrequent behavior, we were able to basically to improve the quality of our models. So you can see that before we had some really bad models that then in the yellow one, the one with discovery, disappeared. So we not only pushed the quality up, so this is precision, sorry, this is fitness and this is precision. We pushed the fitness up, but we also pushed precision farther to the right. Basically, getting closer to this magical value of 1 and 1. Last bit, and then we've done for potential techniques on how to improve your discovery, your process models when you do applied discovery. It's what we call structuring. When we consider process models, the existing models are of existing process discovery techniques are of 2 varieties. Process models that tend to have to focus on the fitness and precision, but produce models that are really complex, or processes that have a low complexity because basically produce models that are structured. So structure means that you tend to have a structure like this one, where basically you have a gateway, something, and then immediately after you close the gateway. So it's easier to identify where you open and when you close the decisions. While in the scenario from before, see, it's difficult. I open a decision here, and then I reach a lot of joins, and then I have another join. So this is unstructured. So there is not a clear entry point and exit point. While in this case, we have a clear, every time we have a clear entry point, a clear exit point, clear entry point, clear exit point. The problem of this models of this type is that they may have a high fitness and a low complexity, but they're also highly imprecise, so they have a low precision. Because basically, in order to guarantee this structuredness, we pay the price of allowing a lot of unnecessary behavior. Ideally, this is something that what we would like to have. So a model that has high fitness, high precision, and low complexity. The idea that we have in this case, how to achieve that, was that instead of focusing on discovering models that are structured to begin with, let's discover models that are really, really good, but could be messy, and then let's try to fix the messiness after. So basically, let's try to see if we can fix this unclear start and end by introducing it later, a posteriori. And in this case, we use a technique that is called RPST, which stands for Refined Process Structure Tree. That's a totally different rabbit hole. Basically, what it does, it takes a process and split this process in 4 components that are called trivial, basically a single arc, a single edge, a polygon, a sequence of things, a bond, where it's basically it's like you have 2 nodes that are sharing, so a set of fragments sharing 2 nodes, so which basically would be like a gateway to 2 activities and another gateway, or a region, which is basically it's like none of the above. It's something that is not clear what it is. So the way it works, for example, in this case, you take a model like this, you start from the top, you say, okay, here I have an entry point, an exit point, and several things in between. So I call it a polygon. And then you go one level down. Now I can see that I have the two gateways with two parts. And basically now in this case, you can consider them as single blocks. So this would be what we define as a bond. You analyze the second one. We have like an activity, a gateway, something, something, a gateway, and an arc. Again, it's a polygon. And basically, you keep repeating this until you cannot analyze anything more. So in this case, we reach this point that we have a rigid. A rigid here because like we have this entry point here, but we also have like this structure in between that basically doesn't allow us to define a clear cut between the upper branch and the lower branch. So this is why this is a rigid. It's like, okay, it's not a single arc, it's not just two things in parallel, neither an arc going into things in parallel. I really don't know what it is. We call it a rigid. Once we have this structure, basically starting from the bottom of this tree, you navigate it backward, and you apply two types of techniques. For structures that are sound, and again, sound means that if you execute this fragment, you're gonna execute a process that will always complete without any problem. So you're not gonna get stuck in a loop. You're not gonna get stuck in a situation where you cannot move forward because you're waiting for something that will never arrive in this type of situation. So if the structure is sound and you are dealing with a structure that only contains end gateways, or you have a mix of gateways, then we rely on a technique that has been proposed by Poliviani in 2014, which basically allows you to structure certain type of process models. Unfortunately, not all of them. So what we did for the remaining situation, which is basically is like, okay, I have a structure where I have only XOR gateways, or I am dealing with a situation with a process model that is unsound. So basically a process model that if I try to execute it, I may end up potentially repeating the same activity 4 times, even though this should never occur. Because, for example, I end up in a loop that constantly produce tokens. So, for example, if I have to make something that is clear, let's assume that the activity is the payment of your salary. Ideally, from the employer point of view, I pay your salary, let's say, once a month. My process is unsound if you end up getting paid 4, 5, 6 times the same month. That's a problem. So that will be an unsound process model. And simply because, for example, like some error in the structure of your process model. And in this case, we extended a technique that was proposed by Olson, and that technique was meant to was proposed in the context of programming languages. So we adapted it for process models, and we also made a few tweaks in order to deal with unsound structure, which in the case of Ullmann's did not exist. And the idea, it's quite simple. So let's say you have a situation like this. You have some gateways. So doesn't matter what type of gateways we have. It could be any type of gateways. But I identify a structure like this, so that I have an activity. So let's say potentially 2 activities in a sequence, A and B. And in between this activity, there is a path that through C jumps exactly in between. If I have this structure, or basically what we can do, at the price of duplicating B, I can move this gateway down and replace, basically, these two gateways get merged. And by doing so, basically, you can see that before we used to have 1, 2, 3, 4 gateways. Now we only have 3. Why? Because basically we duplicate B. If you do this until basically all these weird structures are resolved, and you can also apply it in the other way around. So basically, like, let's say you have the same structure, but this time in between A and B, you are allowed to escape. In this case, what you do, you decide, okay, if you need to escape, don't even go inside, just make the decision before. So what you do, basically, here, you make the decision. Either you do A and C, or you do A and B. But there is no need to escape in between. This is the idea to structure. And again, you do that by duplicating. And this is actually something that you can literally do manually. There is no need for any algorithm. If you have the patience, you can just go on your models and look at this structure and say, okay, I can push this one step backward and duplicate. Or I can push it forward and duplicate. You do this, and basically you can resolve structures like this one. You see these red lines are basically structures that we call unsound, because, for example, you see that you have this end split that theoretically will have an end join here, but as you guys know, the end join will expect 2 tokens, a token coming from this path and a token coming from that path, right? But if in this process, at this point, I decide to go right, I get in, I reach the join, and now I'm stuck. This is one of the situations where basically, like, my process is unsound because I may find an execution that I reach a certain point, I cannot move forward anymore because I'm expecting something that never arrived. With our techniques, by moving this gateway around, we can basically resolve the situation, because what we did, we push this gateway, for example. So in this case, yes, we push this gateway forward. And this D as well. So basically, see, this gateway has been also pushed forward. So you see that there is a duplicate here, while before did not exist. And we pushed, we push anything else in this case? No, that was only the only thing that was needed to be pushed. And basically, by playing with this, the tricky part is identifying what is the element that needs to be pushed. And in general, you start with the most inner one again, and you will discover that based on this tree that we were discovering before. We tested this also in the context of, like, in this case, we used a massive data set with 106 models. We tested it. We compared the structured miner with 2 other existing algorithms, inductive miner, and heuristic miner. And as usual, we measured the 4 complexity measures. And in this case, you can see that, so inductive miner, that is the one that by default tend to produce structured models, it tends to have like several points here in the corner, but it also has a lot of points here at the bottom, where basically means that you have a really low precision. Why? Because in order to guarantee structuredness, you pay the price of allowing behavior that shouldn't be in there. A heuristic miner has a lot of points, tend to be like in the high precision, but sometimes the fitness, it's really bad. This is because you may create these structures that are unsound. And if it's something that's unsound, basically means that it cannot be executed, so you get a fitness of 0. By combining this heuristic with the structuring, basically we were able to somehow find a middle ground between these 2 approaches. So you can see that the yellow points are actually along this line. It's not always perfect. Sometimes you have some bad results, but in general, it's a good compromise among the two. So to conclude, process discovery is not perfect. So my suggestion is never simply take a log, feed it into an algorithm, and take whatever result you get. Always try to improve the dataset, and the dataset often can be improved manually. You don't need anything fancy. In certain cases, by simply removing activities that are infrequent, you're going to notice massive improvement in your results. Try playing with different techniques. Don't always use one simply because it's the same that you always use or because somebody told you that it's the best. Try. You never know. Sometimes you will be pleasantly surprised. Last approach, if you can, try to split the dataset in simple chunks and analyze them individually and then manually merge them, or try to use techniques like destructuring that allows you to basically to improve the quality after a model has been discovered.